Hi, this is Mr. Mac. Now, this video is going to be proofs of the derivatives of the basic trigonometric functions, sine, cosine, and tangent. I don't think I'm going to do the secant, cosecant, and, well, yes, I guess I'm going to do the secant, but I probably won't do the cosecant and the cotangent because they're very similar to the secant and the tangent, but we'll do sine, cosine, tangent, and secant. Now, before we get started with those derivatives, I need a couple of results. And usually when you have early proofs or little proofs that are needed to prove a bigger result, we call those little proofs lemmas. So lemma 1, now I don't really remember if I've done this in a video or maybe just in class, so let's prove it again anyway. Lemma 1 is going to be that the limit as x approaches 0 of the sine of x over x is equal to 1. Now, it is important to state here that x is going to be evaluated in radians. Now, to start out with, I would like you to consider the following diagram. We're going to let this right triangle here represent, well, what is it going to be? We're going to have x as this angle right here. And we're going to let the hypotenuse of the triangle be 1. Now, what I would like to point out is that if we were to extend this side and use the point here, the vertex of angle x as the center of a circle, we could draw an arc, or we could construct an arc down to the line containing this base line, and this arc would have a length of x, because if x is in radian measure is defined to be the length of arc of subtended by a central angle of x. So that arc has a length of x. Now, also, if you look at this triangle, this line segment right here has a length of sine of x, and this line segment right here has a length of cosine of x. And I'll just point one more thing out. This line segment here has a length of 1 because it's the other radius of that circle that we drew from the vertex of x. Now, going a little bit further, if we extend this side, the hypotenuse here, and then construct a perpendicular straight up to that side from this line down here, it's going to turn out that this length right here is going to be the tangent of x. Now let's see if I can explain that. See, maybe I need to put some letters in here. Let's call this point O, we'll call this point A, and we'll call this point B, we'll call this point C, and we'll call this point D. Now, triangle OAB is similar to triangle OCD, obsessive compulsive disorder. Anyway, in a triangle OAB, where the hypotenuse is 1, the side opposite the angle is the sine of that angle, and the side adjacent to that angle is the cosine of the angle. So we get sine of x, cosine of x. So the ratio of opposite side to adjacent side in triangle OAB is sine x over cosine x. Now, the ratio of opposite to adjacent sides in triangle OCD would be CD to DO or OD. Now, DO is 1, and sine x over cosine of x, we know from identities, is the tangent of x. So in other words, CD has to be equal to the tangent of x. And that kind of shows that that's true. Now, from the diagram, if you look at, here, let's take a highlighter here. If you look at this line segment here, this arc right here, and this line segment right here, it should be obvious to you that AB is less than arc AD. The smartboard's straightened that out, but it's really the arc. And that's less than line segment CD. Now, from what we have here, that means the sine of x is less than x is less than the tangent of x. Now, let's do a little bit of algebra here. We have sine x is less than x is less than sine of x over cosine of x. Now, first of all, with this inequality, okay, and now we're going to have to do something here too. We're taking the limit as x approaches 0, and for the moment, let's just imagine we're doing it from the right. Now, it's going to turn out that if we do it from the left, we're going to end up with the same thing. And I may kind of gloss over that part. You may have to include that yourself. But for right now, we're going to assume that x, sine x, and tan x are all positive values. Now, if I reciprocate each one of these, I'm going to get 1 over sine x. No, do I want to do that? No, I don't think I want to do that. Hang on. Yes, I do want to do that. Sine x, 1 over sine x is going to be greater than 1 over x, and that's going to be greater than the cosine of x over the sine of x. Now, what I'd like to do now is I'd like to multiply all three sides of this inequality by the sine of x. Now, once again, remember, since x is approaching 0 from the positive side, the sine of x is going to be positive. So when I multiply through on the inequality signs won't change directions. Now, let me just see if I can clear up the problem here that we're going to have since we're approaching it at the moment just from the right side. If we approached x, if x approached 0 from the left, the sine of x would be negative, and what would happen here would be each one of these inequality signs would change directions. But the long and short of it would be that 1 over x would still be in the middle. It would be between whatever we get on the other two. Now, let's take a look at this. As x approaches 0 from the right, sine of x over sine of x is 1. And that's going to be greater than sine of x over x, and that's going to be greater than the cosine of x. Now, if we evaluate the limit as x approaches 0 from the right of 1, we get 1. If we evaluate the limit as x approaches 0 from the right of the cosine of x, we get 1. And since the sine of x over x is in between those two, its limit has to be in between those two. And so by the squeeze theorem or the sandwich theorem, we infer or imply or decide that the limit as x approaches 0 from the right of the sine of x over x is equal to 1. Now, I'm going to gloss over the rest of this because I did make mention of the fact that the inequalities would change sign, but everything else, sine of x would be negative, and x would be negative, and negative over negative is positive. So I'm going to claim that we believe now that the limit as x approaches 0 of sine of x over x is just 1 whether we approach it from the positive or negative side. And that's lemma 1. This is important to remember now. Limit as x approaches 0 of sine of x over x is 1. Lemma number 1. Now the second lemma I need, lemma number 2. Now I've always wondered, does this make us have a dilemma? Lemma number 2. I want to show that 1 minus cosine x over x, limit as x approaches 0, is 0. Well, the limit as x approaches 0 of 1 minus cosine x over x can be multiplied by 1 plus cosine x over 1 plus cosine x. And this gives us the limit as x approaches 0 of 1 minus cosine squared x. Now I'm just going to write that as sine squared x right off the bat. If you're having trouble with that, go back and take a look at it. You'll agree before very long, I'm sure, that that's true. Okay, and on the bottom I have x times the cosine of x. Now let's write that as the limit as x approaches 0 of sine of x over x times sine of x over 1 plus cosine x. Now if we put 0 in, this becomes 1 by lemma 1. And this becomes 0 over 2, so we end up with 1 times 0 over 2, which is 0, and we have our second result. Now, we're ready to find the derivative of the sine of x. These two lemmas will feature prominently in them, but let's get started. Okay, so we want to find the derivative with respect to x of the sine of x. Well, by the definition, that's the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h, which is equal to the limit as h approaches 0. Let's say equal there. Make sure it's not look like a negative sign. Now, the sine of x plus h, that is not the sine of x plus the sine of h. We have, from trigonometry, an angle addition formula. It turns out to be sine x cosine h plus cosine x sine h, and then we have minus sine x all over h. Now I'm going to group, this by the way is cosine h, not hyperbolic cosine. I'm going to group, what am I going to group? I'm going to group this term and this term together, and then I'm going to group the other one by itself, okay? So this is going to become the limit as h approaches 0 of the sine of x times cosine of h minus 1 over h plus the cosine of x times the sine of h over h. And we're limiting all of that as h approaches 0. All right, now, from our limit, what have we got here? The limit as h approaches 0 of the sine of x is just sine of x. And the limit as h approaches 0 of the cosine of h minus 1 over h is the negative of what we actually proved in the lemma, so we get negative 0. So this is times negative 0 plus the cosine of x, and the limit as h approaches 0 of sine of h over h is 1, so we get sine x times 0 plus cosine x times 1, which is cosine x. So the derivative with respect to x of the sine of x is the cosine of x. All right, now I think I said earlier in the video I was going to do the derivative of the cosine of x also, but I think I'm going to leave that to you all as an exercise. Now, let's go then to the derivative as the derivative of the tangent of x. So what we want to find now is the derivative with respect to x of the tangent of x. Now, we have okay, at this particular point, I want to say that we know the derivative of the sine of x is the cosine of x. We know that one. And I left as an exercise for you the derivative of the cosine of x, but it turns out to be the negative sine of x, and I'm going to use that as well. So we want to find the derivative with respect to x of the tangent of x. Now, an easy way to do this is to say this is equal to the derivative with respect to x of the sine of x over the cosine of x. Now, we know, because we now have proved the quotient rule, that that is the low function times the derivative of the high function minus the high function times the derivative of the low function, and that's negative sine x, over the low function squared. Now, something cool happens here. Cosine x times cosine x is cosine squared x. Now we have minus sine x times negative sine x, so that becomes minus negative sine squared x, or plus sine squared x. And that's all over the cosine squared of x. Now, in the numerator, cosine squared x plus sine squared x is 1. So we have 1 over cosine squared x, and we usually refer to that as the secant squared of x. So the derivative of the tangent of x is equal to the secant squared of x. You need to remember that one. Let's see, now we need to do the derivative of the secant of x as well. So one more here and we'll have our basic trig functions either done or presented as exercises to you. Okay, so we want to know the derivative with respect to x of the secant of x. Now, probably the best way to do this would be to write this as the derivative with respect to x of 1 over the cosine of x. Now, there are a couple of other ways we could do this, but I'm just going to choose to do it this way. Now, we're going to think of 1 as the high function, and it's going to be a little silly, but we're going to do it anyway. Now, that's low, d high, minus high, d low, over low, low. Now, that gives us 0 minus negative sine x, so we get sine x over cosine squared x. And what we're going to do is we're going to write that as sine x over cosine x times 1 over cosine x. Notice the numerator is sine x times cosine x, sine x times 1, and the denominator is cosine x times cosine x. But this is equal to, the first one is tan x, and the second one is secant x. So the derivative of the secant of x is tan of x times the secant of x. And that takes care of our basic trig functions.